Right. Okay. Welcome back. I hope you can hear me and you can hear my voice.
Yes, we can hear you.
Good. Thank you. This is the last part of our tutorial. So I'm going to focus on some spectroscopy. In the tutorial, you can find different spectroscopic methods, and we don't have time to go through all. So I will go through one or two, and then of course you can continue, and now you know how to run computations and you have the basic skills. And I will also talk a little bit about these multi-scale methods, how to run hybrid computations using onion method. And I will also discuss a little bit about conformational search, and maybe some, depending on the time, we can think about some other topics. So to start, I briefly mentioned about the thermodynamic properties. When you run the frequency calculation after optimization, you can get different properties, thermodynamic properties like entropy you can get, and you can get the Gibbs free energy. And this exercise, you compute the relative energy of these different these three molecules. These are three different isomers, and we have the experimental energy difference. So we have the experimental Gibbs free energies, so you can compare computed Gibbs free energies and experimental Gibbs free energies. So it is quite simple actually. We simply optimize the structures and then run the frequency calculation. Here you see, now you know how to read the inputs. Here we use density functional theory and dispersion effects, and this is the basis set, and we run optimization and frequency. Here we give the input file as XYZ file, and you can put your structure in this. So default temperature applied, default pressure applied, and then you get the optimized structure, and you get the electronic energy of your optimized structure, and you can find the 0-point energy. And as you're doing the frequency calculation, you can also collect enthalpy, entropy, and also Gibbs free energy. So all these values you can find in the output file. So you can do this as a simple exercise. And then if you want to check the thermodynamic properties at different temperatures, you can simply include the temperature you want. This is a new and this may be new to you. You can define the temperature required for the thermodynamic property calculation. So it is pretty simple. And if you are working with the potential energy surfaces, as I told you before, your interest is the electronic energy, and don't forget to add the 0-point energy, which is very important. And then you can compare the relative energy, that is the relative electronic energy, including the 0-point energy. And you can do the same for if you compare the Gibbs free energy. In this case, the difference is we include the effect from the entropy, which is very important in some cases. So please make sure that you understand these points. So let's go and work on the spectroscopy. We can start with the infrared spectrum. How to compute the infrared spectrum, and here we calculate the infrared spectrum of benzene molecule. So our input file is very simple. We have here the density functional. We use DFT for the structure optimization, followed by the frequency calculation, and this is the basis set. And this is the charge of the molecule, multiplicity, and then the coordinates. So we can simply run this calculation. Let me try to run it together with you. You can also start the computations with me. Right. So I will prepare the input file. Probably I have the coordinates at the end of the, yeah, here you have the structure, starting structure, you can get it. So as we add the coordinates, we don't need the coordinate file, so you can delete this part. We don't need that. Okay, so that's a very simple calculation, and then we can run it. So our input file is very simple. We simply optimize the structure and then followed by the frequency calculation. So it is running. So now the calculation is finished. So it's a normal termination. If you go up, and you can see vibrational, I mean the frequency data you can find. So, and you can find the IR spectrum in the output file. So you can find the IR spectrum in the output file. So here is the frequency, and what is important is the frequency number here, and also the intensity. So intensity of that is relatively high. So that is a very important peak. And there are two more peaks here. And some minor peaks appear here and there. So, but if you use Avogadro, you can visualize the vibrational spectrum. So let's look at the vibrational spectrum. So if you look at the frequencies, you can see all frequencies have positive values. It means you are on a local minimum, which is good, and we have the optimized structure. In Avogadro, you can go to analysis and plot spectra, and then you will get the infrared spectrum. So this is the infrared spectrum, and we can see now you can analyze the spectrum. So it has 4 important peaks, and we can look at the corresponding vibrations. So let's keep like this. Okay, so we have a peak here around 600, and here you can see the intensity is relatively large, and and if you put the start animation, and you can see the vibration. This is a kind of a rotational motion, right? Okay. And then the second peak is major peak is around here, 3000 to, oh, there are 2 peaks, and you can see stretching, carbon hydrogen bond stretching. Yeah, there are 2 modes. And some minor peaks you can also find. So this is actually very useful for you, because you can really, if you have an unknown if you have difficulties to understand your experimental IR data, you can always compute and interpret your data. So okay, so it is very simple, and you can interpret your infrared spectrum. Now, if you want to get Raman data, again, it is a very easy approach. You can compute the structure. But in this case, we want numerical frequencies. That is important to get the derivative of polarizability. So we should use numerical frequencies. So we use a relatively cheaper method in this case to speed up the computation. And then you can also compute the Raman data in the similar way. let's look at the so this is the Raman So we can run a simple, well, we optimize the structure first, okay, we always do that, and then we compute the properties for the optimized structure. So that's how we always do. So it will take few minutes, and again you will get the Raman spectrum as the output, and then you can compare your computed data and available experimental data. So here you can see the match between experimental values and the computed values are well, it is not really quantitative, but the qualitative agreement looks good. Here we have the vibrational IR data as well, the experimental data and computer data, and you can see nice agreement. Okay. As you are running numerical frequencies, your calculation is a little bit slower. It needs some additional computation, so it takes a little bit more time. And the scaling factor is very important in computing vibrational frequencies. Typically, when you do computations, errors can be made, and there are some systematic studies showing how to minimize these errors. So please have a look at this paper. They describe it. Yeah, so when we use DFT, and it is an open access publication, so you can look at it. They discuss about the scaling factor, which is important to correct the errors coming from frequencies. So I can place this in the chat. I can also add it in the Slack workspace. Right, okay. Let me know if you have any questions. So now you know how to do the frequency calculations and predict compute the infrared spectra or Raman spectra. So Raman computation is still ongoing. So we can come back to this later. Okay, so it is ongoing. It will take a while because you are running numerical frequencies. Similarly, you can try other examples. For example, if you want to calculate UV spectrum, again, it is very simple. You can simply run optimization first, and then you calculate the excitations to get the vibrational excitation energies. So I will briefly explain it. Our objective here, let me find my presentation. Yeah, okay. So we will get the Raman spectrum, and I will come back to this after the calculation. And here you can see an example. Here the idea is to compute vibrational UV and visible, not vibrational UV visible spectrum of these two molecules. So I will focus on only one molecule. And to do that, I propose you first to optimize the structure, because we want a proper ground state structure to compute the excitations. Our objective here is to compute the ground state. I will label this as S0, which is the singlet ground state, and then we do excitations. We compute excitations. This is the singlet excited state, and then we simply compute various possible excitations. Okay, starting from the ground state optimized structure. So what we calculate here is the energy between here and here. So this is called the Frank-Condon point, right? So, and of course there are other excited states. So there are some high energy excited states. This is the second excited state, and there are many more. And then you always look at this the vertical energy, vertical excitation we called, and then we compute maybe we can calculate 30 excitations or 50 excitations and check which excitation is more important. Okay, the first step is again optimization. We optimize the molecular structure. So let's check whether I can copy. Right, okay. So here I have the optimized structure. The input file for structure optimization. I can share this in Zoom. Oh, I cannot share it because too many characters, but I will do it in Slack. So here you have BP86 density functional, and then D4 is the dispersion corrections, empirical dispersion, and basis set, if you do structure optimization and frequency, here you have a new keyword. So this keyword defines the solvent. Sometimes when you do computations, you can apply solvation effects. You can apply solvation effects in two ways. In common practice, when you run quantum chemical calculations, we use implicit solvation. Let me look at this tutorial. Thermodynamics implicit solvation models. You can find this in the tutorial. Implicit solvation is a very common and very successful in many applications. In here, what we do is basically we replicate the solvent by a continuum. Okay, so that interact with the solute and its charges, and it is kind of artificial, but it is quite effective in many applications. So you don't have solvent molecules surrounded by your molecules. For example, if in this case we run the computation in hexane, so we don't have a hexane molecule surrounded by, but we have a continuum to replicate it. So this is called the implicit solvation, and there are different models for implicit solvation. This is called the conductor-like polarizable continuum model, CPCM. So here we are using CPCM, and it can give you it can replicate the solvent in your simulation. So that's quite important because especially if you are working with charged molecules or polar molecules, so the solvent is playing quite important role, so you can always use it. Now please read this in detail, and there are some examples you can try. I will not go through it, so it's for your homework. Now, after doing the optimization, you can get the optimized structure, and that optimized structure you can use for computing UV visible spectrum. In this case, you see, for the optimization we are using density functional here. This density functional is typically good in terms of getting reliable geometries, but this density functional is not good in terms of computing excitations. For the excitation, some other density functionals perform really well, and this is one of them, CAM B3LIP. So this is typically good in computing excitations, and we use triple theta basis set. So for the optimization we use single valence polarization. Here we are using triple theta valence polarization. This is a better basis set because we want accurate methods to compute excitations. So here we calculate 30 excitations. I ran this calculation last night, and I can share the input file with you. It's also available in the tutorial anyway. So I will share it in Slack so you can use it. Okay. And after doing this computation, first optimization followed by frequency, you get the optimized ground state, and then starting from the optimized ground state you can calculate the vertical excitations, and then in the output file you can find the absorption spectrum. So this is the computation. I have done this last night, so you can see. So we are using CAM-B3lib functional, def2 TZVP, triple zeta basis set, and implicit solvation is there, and we compute 30 excitations. And then you will find very important information here. So here is the absorption spectrum. Now in here you can see 30 different excitations, and here you can find the wavelength, and this parameter here is important. This is the this tells about the strength of the excitation. So if you look at the largest value here, you can see that is the largest transition dipole moment. So this has the largest dipole moment. So this excitation is dominant actually. So you would expect an excitation around 180, and there are two excitations, and also this so you can see several excitations with relatively large transition dipoles, around 170 to 180. Okay, and here is another one around 195. You can see another peak, and 261 you can find another one. It is relatively weak. So and let's look at the experimental data. Do we have experimental data? Let's check. Yeah, here you can see so after getting the excitation, you can get an idea about important excitation. You can see, I'm not sure we have any experimental data anyway. So let's look at this paper. So it looks like in the UV spectrum you can see we are interested here in the, let me check. So we are interested in the E form of the structure. So it's basically in the red line. You can see experimental peak around 250, but they were not interested in peaks below 200 nanometers. So yeah, so they only looked at the peaks above 200 nanometers. So then the interesting peak for them is that one. So we can get really close to the experimental value, around 250, and we can see a shoulder coming around 280. So they are talking about this one. So and also you can see some minor peaks around 500, and around 500 you can see peak appearing here. So yeah, and then you can interpret the experimental data. And in my experience, computing UV spectrum is highly challenging because the results are really sensitive to the computational method. And here we are using CAMB3LIP. When you change the method here, so you may get completely different results. So it's quite challenging to compute excitations. And it's always recommended to try different density functionals here. I can propose some methods. So let's check the density functionals. So there are many different density functionals you can find in the manual. When you go into excitations, typically you can use range separated hybrid functionals. So this is a good candidate to compute excitations. Of course, the tutorial used that. Another option is that one, and also LCPBE also good. I usually compute the excitation using different density functionals and see which functional performs better. I also found PBE0 is a good candidate. It has 25% Hartree-Fock exchange, so it performs really well as well. In my experience, and these two functionals, meta GGA, they also perform well in some cases. They have this Hartree-Fock exchange, so that's good in computing excitations. So you can play around with the different density functionals and check which works better for your problem. Right, okay, so and also you can look at different possible excitations. Now let's look at the the most important excitations. So here the most excitation, most important excitation is here. So this is the 1, 2, 3, 4. This is the fifth excitation. So then you can look at the corresponding orbitals in the fifth excitation. So yeah, okay. Now you can see this excitation, fifth excitation, is one of the dominant excitation, and you can see several orbital transition during this excitation. So it's not only one orbital combination. It has 1, 2, 3, 4, 5, at least 6 occupied orbitals and several unoccupied orbitals contribute for this. So it is really hard to interpret what kind of excitation is happening. If it is going from one orbital to the other orbital, it is quite easy because we know the nature of this orbital. We can look at it, and then we can look at the nature of this orbital, and then we can understand electron density transfer is really happening from here to here. But in this case, it is very complicated. So, but there is a technique you can simplify this problem. Then, rather than let me go back to the tutorial. Yeah. So then you can compute natural transition orbitals. Here you see it's a simplified way of looking at this data when you have many excitations to represent single vertical excitations. Many orbital combinations are there. So what you can do is basically to compute these natural transition orbitals, and then you can get a picture like here, so for example, and then you can see combination of all occupied orbitals, and this is kind of unoccupied orbitals. It's they simplified the nature of the excitation, and then it will graphically useful to visualize, and then you can understand the excitation happening from this localized, rather localized nitrogen based orbitals to pi star based these rings. So you can interpret like that. So it is not very simple molecular orbital, but natural transition orbital. So this is a very important technique if you want to analyze complicated excitations. Now, unfortunately, I was not successful in generating. I generated natural transition orbitals, but I have some difficulties to visualize it in my computer. But hopefully, you can follow the tutorial and visualize it. I leave you to play with it. And one important thing is when we compute vertical excitation, what we get is a line, not a peak. But there are techniques you can convert this line into Gaussian function, okay, and then you can really generate a band of excitation, and that you can generate this kind of spectrum, and which is available in Chimera software. It didn't work in my case last night, so you can give a try if you are interested in this kind of problems. And then you can simulate the spectrum, and then you can compare the simulated spectrum with this is the Camby Trilip spectrum in blue, experimental spectrum in black. So you can see the agreement is qualitatively good. Here you can see a shift of the peak And they also have done CCSD type excitations, and you can see now the peak is moving towards the right direction. So it's, you can see a better agreement in this peak, but worse agreement in this case here. So it's kind of moving away. So that's really not good. That's how it is. And theories is not perfect, but you can still understand a lot of things using computations. So I leave you to play around with this. If you are working on excitations, you can use computations to analyze your system. If you have any questions, please let me know. I will give you a few minutes. There is a question. Suppose I have a molecule -1 charge to singlet. I want to calculate its vertical ionization potentials for 4 excitations. So I think we are talking about a different problem. It's not the excitations. So when you say the ionization, I suppose you remove electrons. So I think your question is not really. Okay. Still, your question is not clear to me. Can you explain a little bit more? I will back to you your questions. Okay. So I think we left Raman calculations to proceed, so we can look at the data. Now it's finished, I guess. Yeah, so we computed Raman spectrum. Calculation is finished. Good. And then if you go up, and you can see the Raman spectrum. Yeah, so you can see Raman spectrum, and you can see some important peaks around here. This is the major peak, and okay, you can see some other peaks as well. Okay, so Raman spectrum computation takes more time because we run numerical frequencies. If you go back to the Raman tutorial, so here are the computed data and the experimental data. So you can see a qualitative agreement. It is not really quantitative, but still the agreement is quite good, I would say. How can I calculate the excited state energies? Excited state energies. Okay. So you are talking about the energy of the excited state. So if you looked in the output data, so here is the energy of the first excited state you can find in the output file. This is the corresponding transition. This is the vertical excitation energy. Okay. So let me draw it again. So this is a ground state, a 0, and then we excite. Yeah, this is our so we excite here. This is the ground state, and if you want to know the energy of this point, you can always find it here. And that energy, or that energy corresponding, these two corresponding to this excitation. Okay. Now, if you minimize the excited state, first excited state, you can find the excited state optimized structure here, and then you know the energy of the optimized structure. So, okay, but now here you see the energy of the first excited state, and the energy of the second excited state is here. Okay, so you can find it over here. This is the third excited state, so it's even in higher, and so forth. Okay, I hope I answer your question. Okay, the oscillator strength. Unfortunately, oscillator strength is not shown here, but you can find oscillator strength. You can find the oscillator strength over here. So, yeah, this is the F oscillator strength you can find here. This is the oscillator strength of the first excitation. Shaim, you can speak up. I didn't get your question, so can you explain?
Hello, sir.
Yeah.
Audible? Yeah, actually, I was asking about the vertical detachment energy or vertical excitation energy. First one, whenever any, suppose I have a molecule that is anion and that is anion and that is singlet. So that is a ground state. After the detachment of electron, so it will go on their subsequent excited states. So in subsequent excited state, if the electron is detached, so it will become neutral, and as well as so electron is detached, so it will become from singlet to doublet. So I wanted the energy gap between and one more thing, that excited states are not in relaxed state. Okay, so that phenomena is known as vertical ionization energy or vertical ionization potential, and or vertical detachment energy. The three phenomena, all the things are same. Okay, so I wanted to calculate the energy. Basically, I have seen in many research papers, so they are calculating. So how to calculate? Because this is whenever you in previously about 5 minutes ago, whatever you explained, phenomenon is exactly same. Okay, and one more thing is vertical excitation energy. Okay, so that is whenever electron will reach on the excited state, but it will from singlet to singlet. But the phenomena is same. Like it will be anion, so it will become anion also. Already an anion, but it will reach on excited state without relaxation. So the energy gap, that will be known as vertical excitation energy. So I wanted to calculate how to calculate theoretically. So that was my question.
I'm not really sure I fully understand it, but let me see. So you have the ground state, potential energy surface, and then you excite. Okay. So you said this is a neutral molecule. Is it true?
Yes, sir. Yes, sir.
Okay, so this is a neutral molecule, and you
Yes, sir. This is ground state. Whatever this is anion or neutral.
okay, and you excite, but the molecule is still neutral.
If it is neutral, it's still in excited state. So that
Yeah.
will be known as vertical excitation energy.
Okay.
So how to calculate this? Whenever when we are taking excited electron as well as ground state, both electrons are considered for the calculation. Okay.
I'm not really sure. I really want to understand more. Can you email me detail? We can discuss separately. Okay, I will drop.
Yes, sir. Please share your email ID. That will be
Yeah.
more helpful for me.
Sure. Of course.
Thanks a
I,
lot,
I
sir.
really want to understand it in detail to give you.
Maybe, sir, I'm not able to convey my question properly. Maybe that is the main problem.
Don't worry about it.
Okay, sir. Sure.
Let's discuss it separately. Okay. So you can always come to write me. I will put my email.
Sir, can you write the message in meeting chat? Your mail ID,
You
if
can
it's possible.
spell
Actually, I'm
it.
not using Slack right now.
Yeah. Okay. So I put it in the chat box and also in.
I got it, sir.
Okay. Good.
It is amera.wmc@gmail.com.
Okay.
Is it?
Yeah, you can write me separately so we can discuss.
Sure.
Okay. Now, if you have questions, you can keep asking me until we go to the next. I'm going to talk next about this the multi-scale methods.
Hello, sir. Can you hear me?
Yeah.
Sir, how can I decide whether a particular transition is dark state or it is bright state for UV visible spectrum calculation? Can you explain from the results?
So is it related to the emission?
Yeah, excitation, whether it is absorption or emission, explain anyway, no problem. Means whether from it is transition from one particular ground state to particular excited state, suppose 1, 2, or 3. So whether this transition is in bright state or it is dark state. So from this that calculation, will I confirm the part?
I cannot really answer directly without reading about it. Can you drop me an email separately? Because
Okay,
that's
sir. I will.
I'm
I
not
will
an
try.
expert in it, so but I can look into it. You have my email, so please drop me an email. I cannot really answer that questions right now, so it is beyond my expertise. So,
Okay.
but
Thank
I
you,
can
sir.
read it and I can answer that.
Thank you.
Yeah. Right. Okay. So the multi-scale method. Here we are talking about running computation for relatively large molecular systems. When you do that, one option is to combine two theoretical methods. So this is how we do that basically. If you have a molecular system, large molecular system, you can describe electronically important part using a quantum mechanical method, or you can use and then you can use the remaining part as molecular mechanics or relatively cheaper method. Or in the tutorial we are using XTB method instead of molecular mechanics. XTB is not really molecular mechanics, but it is more like tight binding DFT, or more semi-empirical like. But anyway, the idea is the same, where we describe the important part of the molecular system using quantum mechanical methods. For example, your reaction site or binding site or excitation you calculate in the QM part. Other part you describe using molecular mechanics. This is called hybrid QMMM, quantum mechanics, molecular mechanics. And if you want to compute the energy, the total energy expression is quite simple. Here you have the energy of the quantum mechanical region. Here you have the energy of the molecular, the green part, and here you can see the energy of the interactions between this orange or red part and green part. So that's the interaction energy. So this approach, you can see simply addition of different energy term, and this approach is called additive QMMM. Sorry, my writing is very bad. This is additive QMMM. But there is another scheme which is called the ONIUM. In the ONIUM, what we do basically is to use a different interaction term definition. In this case, we compute the interaction energy term here, this one, as a molecular mechanics calculation for the whole system, and then we compute molecular mechanics energy of QM part, and then molecular mechanics energy of that part. So separately we do, and then if you combine this term here, okay, what would happen? This will cancel off, yeah, and then you will get the following term. This is the energy of the QMMM system. We calculate the energy of the quantum mechanical region, energy of the whole system using molecular mechanics, energy of the quantum mechanical part using molecular mechanics. So this is called ONIUM, or the subtractive. So this is subtractive QMMM. So there are two types of QMMM methods, additive or subtractive. The only difference is the way you define the interactions energy between the two regions. So it doesn't really matter which method you use. In principle, you get similar results. The energy may be not similar, but the relative energies or the properties you get will be exactly the same in principle. But additive methods are relatively difficult to implement because that interaction term is hard to define. But subtractive is quite simple. Now in the tutorial in the tutorial focused on a subtractive method. In this case, we apply quantum mechanics to one part of the molecule, and XTB method. This is more like semi-empirical or tight binding DFT, which is a faster method for the other part of the molecule. So here you can see a very simple example. In this example, what you do is to apply XTB method version 2 to one part of the molecule, and this is the other part of the molecule, and we apply density functional theory. So this is called a two-layer onion because we have two layers, high layer which is quantum mechanical, low layer which is XTB2. And then you can simply run this computation. This is called the multi-scale model because we are using two different methods to describe relatively large molecular systems. So this is obviously not very large. It is very simple, but this is only for practicing, okay? And later probably you have a relatively large, here you have the final tutorial is about crystal, and so it is a relatively large, no, not that one, this one, multi-scale transition. So this system is a little bit bigger, but still not that big, and still you can nicely apply the techniques and you can practice. Now let's try to do this hybrid calculation. I will do, and if possible you can also do with me. The simplest example is here. Our first step is to get the energy. This is energy calculation for this molecular system. So in here, this part we define using XTB2 method. Okay, so here we have XTB method. This must be XTB, so we will check it later. And then we have DFT with dispersion corrections and basis sets for the other methods. And here you describe the QM-MM atoms. Here 0 to 11 corresponds to the quantum mechanics part, okay? 0 to 11, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. These atoms corresponding to the quantum mechanical part. And the is this structure really true? So let's have a look. I just want to look at the structure. Labels. Yeah, okay, so this part is basically this is going from 1 to 12. Okay, so this is true. The first 12 atoms for the QM part. So you first print here the QM part and then the MM part. To run XDB, you cannot run XDB computations by default in OCA. You must plug XDB to OCA program. So it is fairly easy. I will show you how to do that. Let's find the XDB. So there are different versions of XDB. If you print XDB 0, you are using GFN 0 XDB, and you can see the latest version, XDB 2, is GNF2 XDB. So the parameterization in the method is different. But anyway, so what you should do if you want to use this program, so you must take the XDB code from this link. Okay, I can share that link with you. And then you can download the XDB. XDB, there is a file in the bin directory called XDB. This is the XDB latest version, so you can download the right version. I could not really see a Mac version, but they have Windows and Linux. So if you take XDB, this one here, and inside that directory you will find the in the bin directory you can find XDB code. Let's check whether I can download it quickly. Yeah, okay, so I have the XDB code downloaded here, and it has the bin file, and bin has the XDB. So this XDB file you must rename as OTool XDB. And after that you can drop this you have the OCA folder. Oh, that's not. So you can put this file into your OCA folder, which is located in your installation. So you can simply drag and drop this on that folder, and then you can automatically use XDB computations. So I will do one example here. I'm going to use the tutorial example directly. So let me try a different directory. I'm just making the input file for the XDB computation, so I must keep some keywords in the input file. So here I have the input file. I will add some additional keywords. Here I'm running the computations in parallel with 2 CPUs, and I am using memory of 4 GB. I can drop this to 2 GB. So okay, so the computation is running, and it is going to be a fairly easy calculation, I would say. Calculation is running now. It's already finished. So let's look at the computation, and you can see here we are running in the output file. You can see we are running a hybrid calculation, quantum mechanics. We apply DFT with dispersion corrections and this basis set, and we use XTB method for our low layer, and 0 to 11 atoms will be in onium high layer, and we apply DFT, and for the other atoms we apply XTB. So it is a very simple. It's a 2-layer onium calculation, and then you can find information about so it ran, and then you can find different energies. So the total energy of your system you can always find here. Find a single point energy QM, QM2. Now this says QM2. This is because XTB is not really molecular mechanics. It is a quantum mechanical method. So we basically combine 2 quantum mechanical methods. That's why it is saying QM and QM2. So if you want to run optimizations, again you can follow the same procedure. You know how to optimize structures now. So we can simply apply keywords here, OPT, FREQ, and then you can simply run structure optimizations. So this will take a while, I guess. We are running optimization, so it will take time. But anyway, the idea is pretty simple, and you can simply compute relatively large molecular systems. And when I say relatively large molecular systems, it means molecules with more than 100 atoms, for example. I can find some example. For example, here you can see one of my systems. Let me see. Yeah, here you can see, for instance, this is actually a QMMM calculation. I'm not using XTB here, but the idea is the same. This is ONIUM, and here you can see water molecules. This is an ice cluster model, and this cluster, the QM region here has 50 water molecules, so it is 150. So 150 water molecules. And the MM region and the MM region has 112 water molecules. So altogether, so many water molecules, altogether about 500 atoms. So you can see it is a quite large molecular system. So in that case, you can simply apply quantum mechanics in one part of the molecule, and the remaining part you can describe using XTB or molecular mechanics methods. If you use OCA, XTB is easier to use. So that's the basic idea. So you compute very large molecular systems using this hybrid method. And then why you use XTB for one part or molecular mechanics for that part? Because if you try to compute the system with 500 atoms, it's too big for a DFT calculation. If you have a supercomputer, probably you can do it, but it's going to take time to optimize, for example. But if you use XTB for some part of your molecular system, it can speed up your calculation a lot. Okay? So that's the basic idea. Now, if you go back to the tutorial, you can find some example you can play around. So multi-scale, this is a transition state calculation. This is a good example you can do by yourself, and then you can get the transition state for this reaction. So it has two regions defined by XTB, and this part described by a quantum mechanical approach. And you can see transition state calculations through a NAB approach. And then, of course, you can do IRC calculations and get the reaction barriers. So ideas are the same as before, okay? So you can essentially do this is a even larger molecular system. See, so this is nice. You can also try this one, and then you can get more experience. So you can compute transition states for very large molecular systems. So this is quite difficult, I think. If you calculate with DFT, it's quite large. So making one part of the molecular system, I guess in this case they use low energy. I mean, this part probably this is XTB, and then QM atoms 151 to 205. So yeah, okay. So it is nice. You can get the transition states. You can run IRC calculations. I hope you can practice. Now you have the background, so I'm sure you can independently run computations now. So this is what I want to tell essentially. We probably we should summarize what we have done. I can summarize it in few minutes. So we essentially followed a very standard procedure. Our first step was to get the ground state of a molecule. We did this by optimizing the molecule from a starting point, for example here, and then we used optimization algorithms to find the local minimum here. So that was our first task. So we did that. After that, we ran the frequency calculation and make sure that all frequencies have positive values, no imaginary frequencies. So this was our first task. So that is the standard procedure in any application. First you minimize the structure and make sure that you find the local minimum. Our next task was to find the reaction barrier. To do that, we know how to get a local minimum, which is relatively easy, and then we use methods to compute the transition state. So we use NEB approach, and then we located transition state, and then we did IRC. Okay, so it was quite simple, and then we managed to go to the corresponding reactant side and then the corresponding product side, and then we get the reactant and the product. In the reactant and products, when we run the frequencies, we must make sure that all of them have no imaginary frequencies, but here transition state we get an imaginary frequency. By looking at the relative energies, we computed relative energy here. This is the potential energy barrier, and even we can calculate the free energy barrier. So you know how to do it now. So when we have the ground state structure for your molecule, you can compute many properties. You can compute IR spectrum, you can calculate UV, Raman, okay, any property, maybe NMR, okay. So you can do many calculations. But when we have a very large molecular system, we now know how to deal with it. We can define important part of the molecular system using DFT, and then we can use other part using XTB, for example. So in this way, maybe our molecular system may contain maybe 1,000 atoms, and then we can run calculations at reasonable computational cost. So this is what we did basically. So it's quite simple, and I hope you enjoy running computations. There are some other features in OCA which I will briefly mention, may be quite useful for you. How may I delete this? Okay, all right, okay. So some other features, let me briefly mention about it. Now here you can see a nice example about conformational search. You can perform conformational search. Here you can use XTB. This example computes conformations of this molecule. You can simply run XTB calculation and give the coordinates here. You know how to do it right now. So, and then it will compute possible different conformations. Lowest energy conformation is here, and then here is the relatively high energy conformation. So you can get all possible conformations. So this is very nice, because if you work with organic molecules, sometimes conformations can be, very complicated, but this will compute conformations very quickly, and it can be used in your research. So it's so easy. Another interesting approach, maybe, let me see, automated docking. You can do some docking calculations using XTB level of theory. So these dockings can be done for relatively smaller to large molecular systems, and you can get different possible structures, docking structures, and then you can get the relative energy of them. So it's very nice. Here you can see, for example, in this system, we give the guest structure and also the host structure, and then ask them to interact each other. And then the computation gives a different possible combination of structures, and then you can pick up the most stable structure, and then you can look at the relatively stable to unstable structures, and you can collect interesting information. Here you can see preparation of transition metal complex. It's also very nice. You can use this approach. So yeah, this is a relatively large molecular system you can try. You have the background now, you will be able to execute these examples. So I think we have done a lot of work over the past 3 tutorials. So if you have questions, you can bring right now. Okay, a question: is it worth using multi-squares ONIUM DFT XTB, for example, NEB transition calculation to generate the initial transition structure for? Yes, the answer is yes. Your question is about you have a relatively large molecular system, and if you use this molecular system and use DFT to compute transition states, it may take a while. Your idea was to use ONIUM, a DFT XTB method, to get the transition state, and then use that transition state as a starting point to run DFT calculations for whole system. So it's a smart approach. So I would recommend that. So any other questions? Okay, a question. What other methods can be used to improve the accuracy of DFT calculations? Okay, so what other methods can be used to improve the accuracy of DFT? Okay, you remember we have done, we have discussed this to some extent. Let me look at that tutorial. Right, okay. So I must go to our conference. So we have linked this. We linked correlation energy exercise here. Now you see here. Okay, so we are talking about improving the accuracy of DFT. Here you can see the computed singlet and triplet energy gap of methylene, and we have experimental data, and DFT value is fairly close. So the error is about 2.62 kilocalorie per mole. But if you want to increase the accuracy of your computation, you must improve the accuracy of the method. SCS-MP2 is a highly recommended method. It is more expensive compared to DFT if you try to do structure optimizations. But you can optimize structures, I don't know, maybe depending on your computing power, maybe 20-30 atoms, maybe optimized. And also these double hybrid DFT methods also have some MP2 contributions, so they can be used for optimizations. But they can cost a lot of computing time anyway. So one option would be to use DFT and optimize your structure, and then use the optimized structure and compute the properties using high accuracy methods. So this is the common approach. Even in this tutorial, you did that. So we use MP2 optimized structures, for example, to get reliable geometries, and then you can compute single point energies or get accurate energy, or you can even calculate other properties on that optimized structure. So that's how you can improve the accuracy. We don't have a universal density functional, so you may have to check different density functional and see how it performs. But in common practice, in my research, I typically use omega B 97X. There are many density functions, so I typically use omega B97X density functional. It performs really well for my molecular systems. And for organic molecular systems, this Meta GGA M062X also perform really well. Sometimes beats really works really well, but make sure that you include the dispersion effects. But in this functional or that functional, it is not necessary to include empirical dispersion, because these functionals already have properties. I mean, they have a good description for dispersion effects. In terms of the basis sets, choice of basis set here. So there are many basis sets you can find in the manual. Nowadays, the community likes def to TZVP basis set, for example. So it is highly recommended. I use this basis set in my research a lot. Or you can also use a single valence polarization. It is a relatively smaller basis set compared to triple zeta. Again, it depends on your size of the system and the resources you have. It's always a balance between that. I can see another question which is about defining how can we properly define the boundary between QM and MM regions? So it's a very good question. In ONIUM approach, let's find the ONIUM definition. Or maybe I can go into the Gaussian now. Gaussian manual, maybe we can find some useful information. No. So this is a good review paper if you want to learn about the ONIUM method. It uses a link atom to define the boundary. So, for example, the resolution is not good here. Okay, so if you break a carbon-carbon bond, for instance, we can simply add a hydrogen atom to saturate the covalency. So this is actually we don't really break the bonds, but we kind of artificially do it during the computation, and it's always important to add the link atom during the structure optimization or the computation. So you don't need to worry about it, because as soon as you define the boundary region, the program knows program should add a link atom here. So okay, but if you have a situation like this, there is no if the boundary is here, so you don't really break covalent bonds. So in that case, there is no link atom basically. So then the computation is quite simple. But in this case, we always add a link atom. This review is you can read this review about the ONIUM method. It is an open access and I also put this in Slack. All right, more questions. I think the questions keep coming, and I will go through it. Okay, how useful the OCA and XTB in nanoclusters? Suppose gold nanoparticle and few adsorb it like okay. So probably it is nice approach to use. Make sure that XTB calculations are reliable for the nanoparticle, and you can always do some tests and make sure that you don't really destroy the structure or deform the structure during optimizations. You can do few test calculations and see how it performs. And what other basis sets perform better B3LIP? I would say triple theta basis set. So if you can use triple theta basis sets, I answered your question. So you can always get reliable results. Well, I don't know always, but you can get reliable results. When running TDDFT calculations and the keyword lines OPT numerical frequency, the calculation return error terminates the CIS. It is hard to answer that. Please email me your input to output, then I will have a look. I will give you my email here. Emanuele, would you recommend to use AI to generate input files for OCA to study? Yes, of course you can use GPT. So it can generate input file for you, and also you can carefully check the input file before begin computation. So yeah, AI tools are very useful to generate input files, but please double check your input before begin the project. So you can ask more questions if you have, but I think we can conclude the meeting in a few minutes. I will keep the Slack discussion open for next couple of weeks. You can always post questions, and we will pick up your question and try to answer your questions. And Zoom meetings were recorded, and we can share the videos with you, and you can keep it for your reference in case you want to go back and check what we were doing. We always have the email access, so you can send emails, and if you have any questions, we will try to answer. I will circulate a feedback form, and then you can send your feedback to us. It will be very useful for us when we organize this kind of tutorial. We can always improve and make sure that we can do a better job all the time. So I will circulate a feedback form. So I wish you all the best, and thank you for joining our workshop. I hope you enjoyed running computations, and with this background, I hope you will go forward. And we are always welcome. You're always welcome to send your questions for us, and we will try our best to find a solution for your problem. So thank you very much. I will leave the discussion open.